Hello again. This is section 3.1, derivatives and derivatives of polynomials and exponentials. So this is part 2 of section 3.1 of James Stewart's Calculus Early Transcendentals book. So here we're going to talk about the derivative of e to the x. So let's first try to compute the derivative of the exponential function f of x equal to b to the x. Okay, so we're just going to say that for example, it could be a 2 to the x, or a 3 to the x, or a 7 to the x. And so these are exponential functions, and they're not polynomial functions or power rules. We do not want to use the power rule for derivatives on exponential functions. And so here we're just going to start off with noting that what is the tangent or the tangent line's slope at x equal to 0, okay? So what would that be? We'd take f prime of 0. If we took the limit as h goes to 0 of f of 0 plus h minus f of 0 over h, that's going to equal the limit as h goes to 0 of f of h minus f of 0 over h. And since f of x is equal to b to the x, this is going to be b to the h minus b to the 0 over h. And that's just going to be the limit as h goes to 0 of b to the h minus 1 over h. Okay? So now we're going to extend it for the derivative as a function. So we're just going to, instead of using at 0, we're going to replace what's f prime of x, and that's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. If I evaluate b to the x at x plus h, I will get b to the x plus h. We know using exponent rules, b to the x plus h does equal b to the x times b to the h. We see a common factor of b to the x, so we factor that out, and we end up with the limit as h goes to 0 of b to the x times b to the h minus 1 over h. And we know that the limit of a product is the product of the limits. We know that the limit operator is the variable there. H is the thing that is going to 0. So the limit of a product and that constant b to the x can just come out. And so the limit of as h goes to 0, b to the x does go to b to the x. And we just went over this expression here. The limit as h goes to 0 of b to the h minus 1 over h is the derivative at 0. Later on, we're going to learn when we get to the chain rule and also to implicit differentiation that if we've got y equal to b to the x, y prime is actually going to be ln of b times b to the x. Okay, and we do want to explicitly define what e, the number e, is. The definition of the number e is going to be the number such that the limit as h goes to 0 of e to the h minus 1 over h is going to equal 1, right? We want the slope in your e to the x, which ends up being right in between 2 to the x and 3 to the x. It's going to be the exponential function whose tangent line is going to have slope equal to 1. Good. And if we do go back up to this definition, which will appear in any table of integrals, if we have y equal to e to the x, y prime is going to be ln of e times e to the x. And we know that ln of e is log base e of e. And what exponent, e to what power, gives me e to the first power. So we're just going to have that this is equal to e to the x. So it's the only function whose derivative is equal to itself. So what's the derivative of e to the x? E to the x. All right? And the slope of the tangent at x equal to 0 there is, for your function, e to the x is going to be 1. All right. So let's just do some derivatives and practice our derivatives of sums as sums of derivatives. If we've got f of x equal to e to the x plus 5, then the derivative here is just going to be e to the x plus 0, which is just going to be e to the x. F of x equal to e to the x plus 5, if I use my exponent rules, this does equal e to the x times e to the 5th power, and multiplication is commutative. That's e to the 5th times e to the x, and that's just a constant times a function. Remember, if we've got y equal to c times f, y prime is equal to c times f prime. And remember, if we've got y is equal to a constant, y prime is equal to 0. And so we're just using those, right? And if we've got y is equal to f plus or minus g, y prime is going to be f prime plus or minus g prime. Good. So in this example B, the derivative here, f prime of x, is going to be e to the 5th times e to the x. So it's still going to be just e to the x plus 5. All right, I'm looking at f of x equal to the square root of e to the 2x. Using my x radical rules, this does equal the square root of 16 times the square root of e to the 2x. That's going to be 4 times e to the 2x raised to the 1/2 power. And using more exponent rules, that does just equal 4 e to the x. And my derivative here is going to be the constant times the derivative of that function, and that is 4 times e to the x. That's not so bad, right? So you can see where certain radical rules and algebraic manipulations from pre-calculus and intermediate algebra definitely come into play in calculating derivatives. And that's it for e to the x and a to the x exponentials. Just one final note, just know the difference, okay? If we've got y equal to x to a number, then y prime is going to be n times x to the n minus 1. As examples, if y is equal to x to the 6th, y prime is 6x to the 5th. If y is equal to, 4th root of x to the 5th, that's going to equal x to the 5/4, and your y prime is going to be 5/4 times x to the 5/4 minus 1, which is going to be 1/4. Good. If we've got x to a number, we can do that, right? We can use our power rule. If y is equal to x to the pi, then y prime is going to be pi times x to the pi minus 1. Okay. But if we have an exponential, if we have y equal to a to the x, y prime is going to be a to the x times the ln of a, right? So if we have y equal to 2 to the x, y prime is going to be the ln of 2 times 2 to the x, okay? So when x is in the exponent, that's when you use the exponential derivative rule. When you've got taking a derivative with respect to x, and x is the base, and is x to a number, you can use the power rule. And this is our power rule. All right, now I think I'm finished. I'll let you guys go. Next up, we'll be using the quotient rule and the product rule for derivatives, and they are not going to be simple rules. It's not, the derivative of a product is not the product of the derivatives, okay? You have to use a special rule. And we will derive it using, of course, the limit definition.